Okay. Um, so let's get started on the CMOS circuit part. Okay. Now, whatever we have discussed till now, we were trying to use all these, gates. Okay. Now, say you have an inverter. Okay. And then say you have a buffer. And then say you have a AND gate. Now, say you have a NAND gate. Say you have a OR gate. And then say you have a NOR gate and all of that. Okay. Now, so all your circuits, whatever that you are coming up with the design and everything, right? Now, say for example, even this particular design. So this is your schematic. Okay, this is just one of the this path, right? So this is a full design, and then in that design, you may have a thousands of paths. You will get to know everything. So this is we call it as a one path timing path. So register, then combo logic. It can be any cell, and then register. So it's a basic reg to reg, correct? Now what technology that we are going to use to fabricate these basic gates. Okay, so now that is where we are actually going to learn now CMOS. Okay, now anything that you work on all these days, so we have a different technologies. Okay, so you have got like kind of okay, so I'm sure everyone would have read something called BJT. Okay, BJT, and then MOSFET. Okay, and then in that MOS, so you have got a CMOS. Okay, and then now you have got FinFET. Okay, and then now the next future and all of that, say we have it's kind of GAA fit. It's called gate all around fit, and then you also have a MBC fit. Okay, multi-bridge complementary fit. So these are all the families. Okay, that families, transistor families that you can actually choose to build your chip or implement your chip. Okay, now so we don't use BJTs anymore. So it was all we are using it all lot of many years back. Okay, so BJTs are not being used for this current chips. Probably there may be some vendors they may be using, but I have not worked on any of the chips that are kind of completely BJT and things like that. So I have, from my day one of my experience, I'm using CMOS, and now last one decade we have been in this FinFET. Now the future, the next 1 or 2 decade, it is going to be these two guys. Okay, so now end of the day, you have to choose either CMOS or FinFET or one of the family to manufacture your chip. Okay, so now that is what we are going to talk about it. Okay, so we were designing the circuit which is kind of in terms of gates. Now when you look at when you know how do you implement this gate, so it is end of the day you have to make it like kind of transistors. Okay, say kind of you have a gate, say you have a source, and then say you have a drain, or you can just say like kind of say kind of source and then drain. So this is a kind of transistor. Now how you implement your inverter using this transistors. Okay, so how do you implement these buffers using these transistors? Okay, now we were actually looking at only the gate level till there, till now. All these last couple of weeks, we are just trying to understand the digital fundamentals. Whereas now we will be getting into the deeper inside this individual gates. Now, assuming say tomorrow you have to design this inverter, so how you can go and design? What is a circuit that you would choose and all of that? Okay. Uh, so any question here? If you guys have anything that I would just want to clarify it before we go forward. Okay. Now, Let's go and take a look at the basics. Okay. So I won't be covering the BJT because no one is, probably you would have read in the college days in your electron devices paper, and it's not being used anywhere, so we don't need to waste time on it. So what I'm going to do is I'm directly getting into MOSFET. So what is this MOSFET? So MOSFET meaning it is a metal oxide semiconductor. Okay. Now, when I say metal, meaning your gate is metal, and this is oxide, silicon dioxide, okay, and then this is semiconductor, okay. So if you look at this is a cross sectional view, so it's simple thing. So this is your MOSFET, okay. So this is going to be your gate, and then this is going to be a source, and this is going to be a drain, okay. Now this is a schematic kind of transistor level schematic, but the moment you look at this, it is kind of you can see this is a p type semiconductor material, which is silicon, okay. And then you have the oxide. On top of the oxide you have a metal, so it is a metal oxide semiconductor. So that is why we call this as a MOSFET, okay. And if you guys look at, right, like how what are the different terminals that we have in this. So we have got kind of see source, then you have got drain, and then you have got gate. So these three are the main main terminals, or you can call it like kind of main pins or whatever. Now there is a one more which we usually call it like kind of bulk. So that would be always in the center. Okay, so total four terminals if you ask me: source, drain, gate, and then bulk. Okay. Um, Now, what is the source? Source is the terminal which is basically kind of full of energy, or say kind of where you apply your voltage. Okay, it could be voltage VDD or VSS. So your source is always connected to your either VDD or VSS depending on the transistor. Okay, and then what is this gate? So gate is the terminal which controls your switching. Okay, now say this is your source. Now this is your gate. Now say you apply a certain voltage here on the gate. Now the data short, kind of travels, and then your drain gets charged. Okay, basically the data travels. Okay, so now if you look at that is actually a gate which controls the switching. Okay, when the gate is basically at logic 1. So gate when it is logic 1, that is basically switching, or it is we call it like kind of on. Okay, and then there is something called off. So when you have a logic 0, it is going to be kind of we call it like kind of off. Okay, it is off state. Okay, so these two are the states that are very much possible. Now if you look at here, your gate decides whether the transistor is switched on or off. Okay, I'll explain you in a while what conditions and everything. Okay, now as I said, there are different terminals. Okay, source, drain, gate, and then bulk. So bulk sometimes we don't all the time use it, and if you say three terminals also it is okay, but I always suggest you use this bulk also. Okay, now the question here is, so I mentioned it is a silicon. Okay, silicon substrate. There is something like kind of you can call it like kind of pizza dough. So I'm sure everyone knows pizza. So the pizza makers, so they will have the dough. Okay, now that is prepared. Now that is nothing but your wafer. Okay, that is nothing but your substrate. Okay, that's nothing but your substrate. Now that wafer now will be used, okay, to manufacture this. Now the same way here, you have the dough on top of this. Now what we are going to do is you will actually put all the shapes. So it is kind of source, drain, gate, and all of that. So it is exactly the same way. So your silicon is nothing but your pizza dough and anything on top of it. So you have a multiple layers. Say you may have onions, you may have veggies, and you may have you know cheese, and then you may have some chili sauce and all of that. So they are nothing but your shapes. Okay, so that is exactly what we do. So your substrate is basically the silicon. Okay, silicon, basically the substrate is type of it's a silicon type. Okay, now we manufacture the whole chip on the silicon. Okay, now coming back to your MOSFETs, what are the different MOSFETs? So there are two things, right? One is enhancement MOS and another one is depletion MOS. So can you guys tell me what is the difference between enhancement MOS and then depletion MOS? Anyone want to give it a try?
Enhancement mask is when we charge the gate, it will be form the channel. In depletion gate, it will always channel is formed.
Okay. What about others? Anyone want to add anything?
Enhancement is an off condition. The depletion is there always
Okay,
on.
it is simple. It is like kind of you look at this enhancement mode. It is like you try to recollect your switchboard under the bulb. Okay, so by default the bulb is off. Okay, when you want to on that bulb, you turn it on. You turn on the switch. Now the same way, by default this gate is the whole transistor is in off condition. Whenever you want, you try to supply the voltage at the gate and then you make it on. Okay, and then now coming to your depletion, it is assuming that your bulb is all the time on. Whenever you don't want, you off it. Okay. Now, what is the difference? So which one we prefer when it comes to industry? Or when you, so assume you want to design a chip for one of your customer. Now, which one would you prefer in this case?
Enhancement.
Enhancement.
Okay. Reason?
Whenever we want
Drain will be source.
switch to be
One at a
on,
time. No, one at
the
a
it
time, please.
will
One. Go ahead, Pradeep.
is whenever if for example if you on a bulb,
Okay.
whenever we want to on the bulb, in that case only we will turn on the gate so that it will trigger the switch that MOSFET is
No, I
on
understand.
condition.
I
Yes,
understand all that. Now, tell me which one would you choose? Give me exact points. If you have to choose
enhancement.
enhancement, okay, why are you choosing enhancement over depletion?
It will be power consuming perspective and choosing enhancement. Whereas depletion, it will always it is on. It will take power.
Okay.
Uh,
I got what you're saying. Okay, so the way so these are all the basic understanding that you guys should have. The thing is that you choose enhancement mask because whenever you want transistors to switch, only that time you make it on. Okay, not the other way. So it is always on all the time. Okay, and whenever you don't want, you don't go and turn it off. That is not the way we do it because when it is kind of depletion mass, there are chances that your power consumption would be on the higher side since we are actually implementing or a lot of different chips, right? Say you may have a chip that is goes into your mobile or pad or battery operated devices and all of that. So your power consumption is also an important factor when it comes to the transistor type that what we choose. Okay, and also it depends on what type of design that we are working on. So assume that you have both options, but I would actually go with enhancement, because that is what will help me to reduce my overall power. As simple as that. Okay. Okay, now a simple thing we just discussed, right? Now this is your source. Okay, now this is your gate and this is your drain. Now assuming you turned on the gate is on. Now there are charges that will travel from source to drain. Okay. Now at how much time this drain becomes full? How much time does it take to become completely to equal unto your VDD level? So that is something that we call it propagation delay. What is this propagation delay? Propagation delay. What is the meaning of propagation? A simple meaning of propagation delay in digital world.
It is the time data goes one point to one point.
Uh, so it is basically the amount of time it takes to charge this drain. See, the moment your gate is kind of turned on, now the charges travels and then becomes completely or equivalent to your VDD or whatever it is. The drain gets completely charged. Now that time is what we call it like kind of propagation delay. Now your propagation delay, say for example you have a inverter. Okay, now this propagation delay, say for example 20 ps delay. Okay, delay, say it is 20 ps. Okay, now so if you want to reduce this propagation delay, or this delay depends on what parameters. Say I want to bring it to say 15 ps. Now what is that you have to do so that your delay would be 15 ps, or I want to make it to 30 ps. Okay, I want to increase the delay. Now what is that you have to do so that your delay can be reduced and your delay can be increased?
Distance between source and drain should be lower or larger, I
Okay,
think.
okay. What about others?
Yes, by changing the distance between source and the train, we can change the delay.
Okay. Anyone else want to add? There is a better term to it. There is a better term.
Scaling down the channel length.
Okay,
You
so
have to
that
reduce the channel length.
okay, so that is no. How can we reduce the channel length in a
There's a there's a term called as width to length ratio.
okay. So exactly. So now you guys have to understand any transistor that you talk, they have a W by L ratio. There is something called width, and then there is something called length. Okay. Now based on that only, we actually kind of decide uh, whether it is going to you know your basically a simple thing, your delay depends on your WL ratio, as simple as that. Now you might wonder, there may be a threshold and all other things, but I gave you guys a question, right? What is the meaning of drive strength? You guys remember what is the meaning of drive strength?
Yeah,
So what
Yes,
is
sir.
the drive
Yes.
strength? What is the meaning of drive strength here?
it's a capability to charge or discharge the load.
Much faster
No,
way
no.
or in a slower way, so you can pick whatever that you want, right? Now coming to this simple circuit, so this is your schematic. Okay, this is your schematic. Now the corresponding the 3D structure is this. Okay, this is the corresponding 3D structure. Now try to understand that this is basically your source. Okay, and this is your drain. This is your, sorry, not drain, gate, and this is your drain. Now As simple as that. What is that you see here? There is a distance between source and the drain. Okay, this is something that we call it as a channel, and that channel is controlled by your gate. Correct. The channel is controlled by your gate. Now, this is something that we call it like kind of channel length. That is something that we call it as a channel length. Okay, and then if you look at here, this is something that W, that's called width. That is something that we call it as a width. Clear? Now you can actually understand, try to understand that, so you are actually going on the road and there is a small bridge. Okay, say you are actually kind of going on the road. This is your road. Now on top of it, see, you have got a bridge. Okay, now this is something that I call it like kind of L length, and then this the width of the road. Okay, that is basically the transistor width. So now remember, you have a small road, the small width, say only one vehicle can go at a time, and there is a bigger road. Now which say for example, simple, you have 100 vehicles here and they have to go from here to here. Now so there is a options, one road, one track, two track, and things like that. Now assuming there is a one track road and then there is another road with two tracks. Okay, so this is one track and say this is two track. Now which one will go faster? So we assume all the 100 vehicles will have to go one by one, or leave at the same time. Now which one will give you lesser time and which one will give you more time? How much time it will take? Now I'm just trying to I'm going to ask you, right? Which one will be kind of having a short time?
Second one.
Second one.
Okay, now that means what? You have a bigger width, the road is kind of bigger, so your charges can travel. Okay, you can actually, they can travel like this. Okay, now imagine if you have a width which is smaller. Okay, assume you have a width which is kind of say smaller. Now in that case, your charges will not be able to travel much faster because there is a limitation. Now, assuming, see here, this is your width. Okay, now you will have only this area for the charges to travel, but whereas when you have a bigger width, you will have a bigger area where the charges can travel. Now that is why we say your delay depends on your W and L of your transistor. Okay, now this is, remember, this is in terms of transistor level. Okay, this is in terms of transistor level. Clear? Now a simple question, when you have a, so how delay varies with respect to D and L and W? How your delay varies with respect to W and L? When W increases, what happens to your delay?
Inversely proportional.
No, let's go one by
Delay
one. So when W is high,
decreases.
what will happen to your delay?
Decreases.
Delay is less.
Decreases.
Delay decreases.
Okay, now when the L is actually high, what actually happens to your delay?
Delay decreases.
Delay
Delay.
Increases. Directly proportional.
increases. Okay, so
Yes.
how how it is increases?
So it will take more time to electron from source to drain.
So when your length is on the higher side, the charges take more time to travel from here to here. Okay, say it is kind of you traveling 1 kilometer and you traveling 2 kilometers, something like that. Okay, so your actually delay increases when your length increases. And now you guys try to understand, when you scale down the technology, say 40 nanometer and 28 nanometer and 16 nanometer, and then say 7 nanometer. Okay. Now, what is this meaning of all these nanometers?
W by L.
Distance between source and drain.
Distance between source and drain.
Distance to source and drain. That's
That is okay. Now, assuming the same cell, say you are actually going for an inverter which is manufactured in 40 nanometer, and you have an inverter that is manufactured in 28 nanometer. So this is 40 nanometer. Assume this is a inverter X1, and here also the same inverter which is 28 nm inverter X1. Now, what would be the delay? How the delay would be?
Delay will be decrease.
Where?
Second one.
40
The
nanometer, more delay.
28
I,
nanometers.
Go ahead, guys. Someone was trying to answer it. Go ahead.
can I say?
Go ahead. Go ahead. Go ahead.
For example, the first one 4 ps, the second one 28 ps. It is much faster
Okay.
because of VL divided by L, because of my suggestion.
Okay. Now, what about others?
40 nanometer delay is more, 28 nanometer delay is less.
Okay. Now, if you guys look at right here, okay. Now, so you guys have given me a rough idea or answer. I can say, when you are going from higher technology to lower technology, what is it you are trying to achieve?
Delay time, propagation delay is decreases.
So basically, your performance can be improved. Agree?
Yes.
Okay.
yeah.
Now, let me give you a homework. I want you guys to compare 40 nanometer and 28 nanometer. Compare, okay, 40 nanometer and 28 nanometer. And I want you guys to list at least 5 to 10 different points that, okay, so in 40 nanometer, this is how it is, in 28 nanometer, this is how it is. And, this is the performance. This is a kind of, area, power, performance, area, and all of that. So try to compare the two technologies. It's simple, right? Like, let's say, this is what I do in my work. Say I have got kind of 5 nanometer and I have got 3 nanometer. In three itself, you have got N3, you have got N3E, and then you have got N3P. Now remember, all these are 3 nanometer only. But now, what is the benefit if I choose this particular thing? Is it better than this? Okay, so I have to look at your PPA. How is the, what are the other things that I need to look at? How is your power, performance, and then area and manufacturing cost? Okay, manufacturing cost. Okay, and how much it is going to be and all of that. So I want you guys to go and try to understand. Okay, if you are, say you have a chip, now your customer is asking you to reduce the power or reduce the chip size. Okay, because he's feeling that it is disturbing his product. Okay, he's asking you to bring it the size down. Now, which one will suit you? How will you decide? That is a basic thing. Okay, got it. So that's your kind of homework. Okay, so we have covered W, L, and the delay and all of that. Now we also have covered something on the drive strength part. Okay, now what is that going to be in lower drive and what is it going to be in bigger drive? So what is that decides your drive strength? What is that decides your drive strength?
With
So your WL is the one which decides. Ideally speaking, lower drives will have a smaller width and higher drives will have a bigger width. As simple as that. Okay. Now That is why I said lower drives will have a bigger delay, and if you want to bring it down, the delay, increase your drive strength. Okay. So your assignment or homework, see in a timing critical path, which drive strength you prefer to use, and when you have a non-timing critical path, which drive strength you will try to use. That's your homework. Okay. Moving on now. So any question in this slide? Because these are all the very basic things. So how your mass is structured and how it will be in silicon, and what is this W and L, why we need to know, and how WL plays a bigger or important role in coming up with the different drive strengths and etc.
Can I ask a question?
Go ahead.
What is the purpose of bulk in here?
Okay, so how will you prepare a pizza without dough? The base. Will you be able to? Would you be able to prepare prepare a pizza without the base dough?
I understand. I understand. I understand.
That is basically the silicon. That is nothing but your bulk or substrate that we call it.
Substrate. I understand. Okay.
Yeah.
Okay.
So this P-type body that we call it, no, that's nothing but your substrate. Okay. Yeah.
I
Okay. So MOSFET
Can I,
operation. Sorry. Go ahead.
can I ask a question, sir?
Go ahead. Go ahead.
So that propagation delay will only depends upon the width to L ratio. I mean, like, or else any other components like capacitances.
At the transistor level, it depends only on these two things. Okay. And but remember, your delay again depends on your threshold voltage and then temperature. There are many other things as well, but if you look at your individual transistor level, only the two things defines your whole properties. They play a
Hmm.
major role. That's the basic thing.
Okay.
Okay. Yeah.
can I ask another question?
Yeah. Go ahead.
Should we know the schematic of this, or
You
should we
should. I would be
design
covering
it?
everything. I would be covering everything. How to design a schematic and everything. We
Okay.
will cover. Nothing to worry
Okay.
about.
Okay.
Because
Okay.
let's understand the basic mass operation, and then we will also try to understand the basic second order effects, and then power dissipation, and then different power components, and then we will get into the schematic parts. Okay.
Okay. I got.
Okay. Yeah. Okay. So the modes of operations. Okay. There are, when you look at your mass, there are three modes of operations. One is cutoff, second is linear, and third is saturation. So when you say cutoff, it is basically your gate voltage is basically less than your threshold voltage. See, there is something called a threshold voltage. When the gate voltage is higher than the threshold voltage, then only it will actually on. Okay, the gate will turn on. Okay, otherwise it will be kind of off condition. So that means the transistor said to be in off condition. Okay, when it is in cutoff, and your output current, that is basically your drain current, that would be kind of um, zero. Okay. Now coming to this one, linear. So you have got, when you wanted to turn on the transistor, your voltage will be, the gate voltage would be slowly increasing, and then when the voltage is greater than VGS is greater than VT, your transistor is said to be in said to be in on condition. Okay, but remember there is another condition where this is another condition. When this is satisfied, the transistor is said to be in linear. Now the third one is basically a saturation, okay, which is again on conditions. VGS is greater than VT, on condition, and when this here it is less than or equal to VGS minus VT. Now your drain current, the drain voltage is greater than VGS minus VT. So that means it is kind of saturation. So when these conditions are satisfied, so we have, as I said, three modes of operation. One is cutoff, and then I have got linear, and then say saturation. Now when you say cutoff, transistor is said to be in off condition, so your output current, that's basically drain current, is zero. And when it is in linear mode, it is basically your gate voltage is greater than your threshold voltage, and your VDS is less than or equal to VGS minus VT. Okay, when this condition is satisfied, it is said to be linear. And saturation meaning, again, your gate voltage VGS is greater than VT, but your VDS is greater than VGS minus VT. All right. So when this, actually you don't need to buy heart it, but it's just a small formula, so you can actually write it in a notebook or somewhere, your quick interview guidance. So just before getting into any kind of interview, you can just quickly watch out this. And when your device is in linear mode, this is going to be your output current equation, which usually I normally not a fan of these equations that you can actually get, nobody would ask these equations. I have not seen people asking it, but I have also kind of seen one or two guys who are kind of digging into it and trying to solve it, and which I hate the equation, as simple as that. So you don't need to worry about what is this IDS and all, but understand how the mass operates. Okay, as simple as that. Okay, so any question here? Okay, now let's get into in depth of it, what it is going to happen in each of the things. Okay, now see, this is your cutoff. What is the meaning of this cutoff? That is basically the channel. It's basically, since it is a p-type body, it is completely filled with holes. Okay, it is completely filled with holes. Okay, and now there is no channel formed here, so the charges which are sitting here cannot travel here because there is no channel. So that means what, your ID is basically zero, because there is no channel formed. And why channel is not formed? Because your gate voltage is less than your VT, threshold voltage. Okay, now that is what we call it like kind of cutoff. And next one is something that we call it like kind of active. Now what is meaning is, your VGS is greater than VT. Okay, it is greater than your threshold voltage. Now what is this meaning? Your channel is basically formed, so the holes that were there very close here, they are all kind of pushed down. Okay, so we have actually now kind of channel is formed. Now when the channel is formed, now the charges can flow in this channel. Okay, now this condition, as long as this condition is true, okay, it is going to be kind of set in linear mode. Okay, set to be in linear mode. Okay, so it's basically simple. Channel forms, electron flows, your IDS increases with VDS, because both drain current and your drain voltage increases. That's the main thing, because they both kind of linear. Okay, when it is in linear mode. Okay, the next one is basically your saturation. Okay, now what is the meaning of saturation? The channel gets pinched off the moment this condition is satisfied. Okay, the channel gets pinched off the moment it gets satisfied. This condition is satisfied. What does this meaning is? Your current is constant. Your current is going to be constant irrespective of your drain voltage. That is the meaning. Okay, now the channel pinches off, your now current becomes independent of VDS. Now in the linear mode, what, they both were increasing like this, but in saturation, irrespective of whatever it is, your current is constant like this. Okay, so you can see kind of, we current saturated, and then that is what something that we call it like kind of, constant current source kind of things. So it's a kind of current, constant current. Okay, now these are all the three modes of operations that any MOSFET will have. Okay, now remember one more thing: when someone is asking you an interview, whatever that I have explained, you just try to explain the same thing, which is okay, which is kind of, good enough for you to, impress the interviewer. Now it's not just only this three thing. Now you have to explain it with this IV characteristics, and which will actually help you in a better way of explaining. Okay, now simple, right? Your I is basically on the Y direction. That's a drain current, and then you have a VDS. That is a drain voltage. Okay. Now try to recollect what and all we discussed. ID when cut off, right? What is ID? What is the ID in cutoff?
Zero.
It is zero. So now, what is this meaning is your cutoff is in this, because your ID is zero. So when the transistor is in cutoff, okay, your ID is basically zero. So this is the area where you will have your, the current. It's because zero, ID is zero. Now in linear, what it is?
The ID increases.
So linear, it is basically your both drain voltage. This is your drain voltage and your ID. Both voltage and current increases. Now you see here, okay. Now the area where both of them are kind of increasing linear. Now if you look at here, so you can actually draw something like this, some area like this. Now what is this meaning is, this area is said to be what? Linear. Okay, this area is said to be linear because both voltage, this is on the x-axis, it is increasing, and your y-axis also increasing. That means what? Both voltage and current are increasing. That is the reason we call this as a linear region. And then now what about your saturation region? What it is? Constant current. Current is constant. Now look at here. Now look at here. Okay, both of them are increasing here, right? Now the moment it reaches this, beyond this threshold, linear, what happens to your voltage? Drain voltage increasing, but what about your current? Is it increasing or it is constant?
Constant.
Now look at here, so this is also the same thing. Okay, the current is now constant. Okay, so this area, so your cutoff is at, ID is zero, that is a cutoff, and when it is increasing, both voltage and current increasing, that is something we call it like kind of linear. Okay, and the moment it crosses that, and the transistor is, when the current becomes constant, the MOSFET or the transistor is said to be in saturation region. Saturation. Okay, is that clear? Any questions here? So you should actually explain with this IV characteristic. Remember, you can just mark this, but remember this is different gate supply. Gate. This is a different gate supply things which you can actually explain. You may have a different VDDs, right? So it is going to be say something like this. Okay. So any question here on the three modes of operation under this IV characteristics?
The MOSFET will work in linear time. It will be affect our time operation or not.
I did not understand what is it, your question.
Our MOSFET will work in linear, right? Linear
It will
position.
work on all three cutoff, linear, and
Linear and
sat.
saturation.
Yes,
We are using on for saturation, off for cutoff. But
correct.
linear, it will act what like
No, okay. So now coming to, so I will tell you what modes that as a digital chip designer we prefer. Okay, uh, I will answer you that. Just wait for a minute. But I wanted to understand if anyone has any kind of question on basic operation. Okay, moving on. Okay, now the simple thing is there are three modes of operation. Now, what is that digital engineers, digital chip designers will use? Now, remember, we always prefer either cutoff, okay, or saturation. Okay, we try to maintain the transistor when you are designing a digital chip, digital implementation. Either it is zero or one, as simple as that. We don't have anything between them. Okay, either it is zero or it is kind of one. There is nothing that you'll maintain it somewhere over here. Okay, so for digital designers, we always maintain either it in cutoff or in the saturation. Now, who uses this linear? So the analog designers. So the analog or mixed signal designers, they use the linear mode because they bias it. Okay, so they do a lot of biasing and different techniques and all that. So they are the one who uses the transistors in linear mode when they implement their designs. Okay, did I answer your question?
yeah, yeah,
Okay,
thank you.
okay, all right. So your homework. Okay, now what is strong zero? Okay, and strong one and weak zero, weak one. Strong zero, strong one, weak zero, weak one. Okay, this if you understand this, you will be able to now go and easily understand. There is something called pull up, pull down, and all of that. This is your homework for the next week. Okay.